So today, thank you for attending. I'll be speaking about writing unit testing for data science code and how this can help you with writing production level code for your projects. We can use this as well. All right, so just a brief introduction. My name is Nile Wilson, Senior Data Scientist at Microsoft within the Industry Solutions Engineering Group. So the reason why I'm giving this talk today is that from a background in academics, I wasn't really writing any sort of production level code at the time. So once I joined Microsoft, it was a big learning curve, and I had to learn a lot in the past few years, but I'm really happy with where I've come, and I'm writing code that is being used in a lot of different customer solutions. So within Industry Solutions Engineering, we work with different enterprise customers to build cloud-based machine learning and AI solutions. And so I've worked in a variety of different industries, a lot of different ML domains in the past few years, and my learnings that I'm sharing today are from all these different experiences. And just side note, as Sean mentioned, PhD in bioengineering, specifically with brain-computer interfaces. So if anyone's interested in that, also feel free to reach out. All right. So what I want to get across in today's talk is highlighting the value of unit testing specifically for data science code. It's a concept that exists within software engineering, the software engineering realm, and is not universally applied within data science currently. So I want to help kind of improve the use of unit testing here. I'll be covering the key concepts for unit testing as well as some specific techniques for how you can apply it within your work, and hopefully empower everyone here to start writing tests if you aren't already. Okay, so I just want to start off with a basic case study. This is an actual project that I worked on a few years ago with Warner Media. So Warner Media, think of Warner Brothers, Universal Studios, like just the big media company. And so when you're filming a production, let's say a TV show or a movie, there's a lot that goes into it. And when you're filming, you might have something called a digital daily, which is when you have footage running continuously from the start of your day in production all the way to the end. So just one continuous roll where you're having multiple takes and multiple scenes. So with this, it's a long form video, and when it comes to archiving purposes, you don't necessarily want to store absolutely everything. That would cost a lot and take up a lot of space. So with Warner Media, they're interested in helping their archivists more efficiently determine when there are areas of interest within the footage, so when specific scenes or takes are happening, and then discard the rest that's not really of interest or won't be useful. So in this case, the project was to use machine learning to be able to help create timestamps to help them, the archivists, more effectively scrub through the videos and determine what to archive and what not to. So with this example here, we're just showing that we have raw footage and high-level overview. We have audio workstream, computer vision workstream, and a metadata extraction kind of substream from that. Everything then gets consolidated and generated into the timestamp report. However, this is just a high-level overview. If we go a little bit further, here we go, we can see it's a bit more complex. Each of the blocks here are different steps within a pipeline that are processing the data in some way. There are multiple data scientists working on this project at the same time. And I realize this is small. You don't need to actually be able to read the text on here. It's just to show that it's a lot. And if you're interested in learning more about the solution itself, we do have a blog post at aka.ms/CSE Warner Media Action Cut. But with this, we can see it's complex. There's a lot of spots where there's data being read in and out from different locations, code. Each of these blocks are essentially a different Python script, so .py files, and there's a lot happening here. So with this sort of solution that's complex, multimodal, a lot of people working on it, how can we quickly pinpoint errors? When something goes wrong, how can we quickly address that? Are we confident in the code that we're merging in? And also, do we get consistent and replicable results? So there's a lot that goes into that, but one of the major things that can help address a lot of these issues is unit testing. So what is unit testing? When it comes to unit testing, it's essentially making sure that every little piece of code or each unit is working as expected. So you can think of it as like a quality check, making sure each of the gears in your clock is working, like a small part of the broader solution. So this is really helpful for collaborative coding in particular, but it's also useful for when you're just writing code for yourself as well. So it really helps with reproducibility, as well as helps reduce debugging time, and it's just generally like a really good practice. I do want to take a moment to note that there are other sorts of tests out there as well. There's integration testing, smoke testing, et cetera, which are also important, but today I'll be focusing on unit tests in particular. Okay, so when are they written? This depends on who you ask and what sort of work that you're working on. So if you're doing a lot of exploratory data analysis and not moving things to production, you might not be writing tests a lot depending on your practices. However, if you're working on a lot of production level code, writing things to go out to be deployed using CI/CD, then you're most likely writing unit tests at that stage. So depending on who you speak to, there are different opinions on when you should write them for various good reasons. So in this example here, we're showing the different highly generalized flow of a machine learning or data science lifecycle. You have exploratory data analysis to proof of concept development, minimally viable product to production. And so for the first few steps there, we see that unit testing is optional. It could still be helpful for what you're working on, but is not usually required at that stage. When it comes to creating the minimally viable product, it's definitely encouraged that you start writing tests at this point if you haven't already, just to ensure that as you're getting ready to go to production, things are already nicely in place. So alternatively, there is test-driven development as well, or TDD, which is the practice of writing the tests first or kind of immediately as you're writing your functions that you're going to be testing. So this can be really helpful, but when it comes to the nature of data science work, a lot of stuff's really exploratory. We don't always end up using the code we write in the beginning in the end. So for some people, they recommend not doing this at the start to save on time. So I'm kind of at the camp that if you're in the very beginning stages and you're not sure where things are going to go, if you're short on time, then I would recommend saving the unit tests for later, but happy to discuss that later as well. Okay, all right, so let's get into some general concepts about unit testing. So there's more that can go into this, but just for the sake of time, I'm going to group this into four high categories, and starting with clean code. So in this presentation today, I'm just going through a very basic example of a class that I wrote called Produce Insights. Very basic. It's not really like anything at all, but just something for demonstration purposes. But the purpose of this class is to be able to take in produce sales information and do some sort of calculation giving that data. So with this example code here, we can see that in general, when it comes to testing, we want to have our code organized in a clean manner. So instead of having everything within, let's say, a single large script or a notebook, for example, where you're not organizing things into different methods, you'll want to clean that up a little bit first. To have distinct units or your methods that you're writing, you can organize those into classes depending on what is appropriate. And key thing is for each of these methods that you write, you want to ensure that you have doc strings, which I know is very basic, but just a reminder for everyone that these are always helpful for making sure that we understand what the purpose of a function is, as well as what the expected input and outputs are. But type hinting as well to make it easier to know what the expected type is for anything that's coming in and out of the method. Just want to also mention that there's a lot of different styles for doc strings, as some of you may be aware. So just use whatever is preferred by whoever you're working with, or if you get to set that preference yourself, just use whatever you like. Okay. So when it comes to writing the tests themselves, the tests are usually written as another method. So we have a Py file that's specifically holding our tests, and we define our tests as, let's say, test underscore name of our function, and whether that's going to be happy path, as in if that's for how the performance should be if things are working as expected, like in terms of the input being correct, or exceptions, like if things are put in incorrectly, what's the expected output. So for all these tests, there's a few different ways of writing these, but I prefer the 3 A's method, where we start with arrange, move into act, and then go into assert. So what we're showing here is that in this test we have this arrange section which focuses on organizing any sort of input that would be passed into the function itself. So we're testing a method called load data here, as you can see with the name test load data. So the method load data from our Produce Insights class takes in some sort of data path. And in the range section, we're just setting that data path to some path locally that we have source data in. And the expected output, we're just going to be reading that in as well, and then arranging that here, such that when we get to act, we can load in that data path. And lastly, for assert, this is where the actual functionality of the test happens. This is making sure that the output that we get is as we expect, given the input. So in general, when it comes to tests, we follow this basic structure. All right, so what is data science without data? We got to have data, right? So when it comes to working with tests, we are focusing on testing the functionality of those methods themselves, and not necessarily about, what is the what are the actual values we're getting out of the data? What is the confidence? It's more about the functionality. So we don't necessarily need to, nor do we want to, run tests using the full data each time. That would be really inefficient and take a long time. And in addition, tests are usually run locally as well. So that data has to be stored locally. Depending on the size of data that you're working with, it's not really feasible to check in all that data into a Git repo. Like, you would not want to do that. So for sample data, we usually either take a subset of our existing data or use open source data or create synthetic data. Just a thing to note is, depending on the data you're working with, it's likely that you won't be able to store that directly into the repo for privacy or security reasons, for good reasons. And so when it comes to determining a sample data set to use for testing, you want to make sure it's representative of what you would actually be running the full code on, and also covers edge cases as well. So when it comes to selecting samples, you got to make sure you have a good distribution, and if you're using open source data, just make sure it has the appropriate licensing. And when it comes to synthetic data, just make sure you're covering those different cases. So in terms of an example of sample data I had to use recently, this is a project I worked on where I was contributing to an open source Python package called Presidio. So Presidio is for data de-identification, and they have an image de-identifier in beta. But I realized there wasn't any sort of compatibility for medical images, since those are of a different image format. So I was working on this DICOM medical image redactor, so for redacting any sort of sensitive text. Note that this is using open source data, so what we're seeing here is not actual patient information, it's synthetic patient information. But with the solution here, when I was ready to submit this to the open source library, I needed to make sure I had some sort of data with it to be able to test the functionality and prove to this open source library, hey, what I'm adding into your package here actually works and will work consistently. So the data that I use for development, and as well for in the unit testing, is this open source data set from the Cancer Imaging Archive, specifically for evaluating DICOM de-identification. So the license on here was good for us to be able to use it, but just to make sure, I also reached out to the data owners to see if they're comfortable with us using a subset of their data to host within the repo for testing and demonstration purposes. So luckily, they were really excited about it, all good, and so we have the data within the repository for the test being run. So when we were interested in getting that data into the repository as well with the unit tests, that was done via, of course, a pull request into the public repository. And so through pull request or PR builds, you can use that to automatically validate that your tests are passing before you merge any sort of code into your main functioning branch. So this is typically set as a policy within whatever platform you use, whether that's GitLab, GitHub, Azure DevOps, whatever you have. And this is just a nice way to ensure that you're never going to be making a change to a branch permanently that is going to, or not permanently, sorry, not making a change to one of your main functioning branches that's going to cause any sort of breakages. So this is great because it blocks PRs from being merged in if tests are not passing. But it's also a great way, not just for you to see if your changes to your own code are no longer going to be working with the code in the repository, but it's great for collaborative purposes as well. If you are working on someone else's code, for example, let's say someone has a function within the repository that you want to expand upon, or you feel that there's some edits that could be made to fix a bug. You want to ensure that whatever changes you're making don't break the unit tests that are being run on that function. Unless you feel the unit test itself is flawed, then you can change that as well. But it's really great for being able to ensure quality when working for yourself and also with others. All right, so going into specific writing techniques. These are basic techniques that can be applied for unit testing in general, but I'll be going through this through the lens of data science projects. All right, so let's start off with fixtures. So on the right-hand side, we have an example of a test, or actually, sorry, part of the test Python file where we're seeing multiple different tests. So because we're working with that Produce Insights class, there's multiple methods within a class typically. So if we're testing multiple methods within a class, that means we're going to be using an object of that class, multiple times. And to reduce redundancy, we can create a fixture or an object of that class and just use that one fixture throughout the whole test suite. So up here, we have a definition for a produce fixture. That's going to be an object of our Produce Insights class. And so this fixture itself is going to be passed in to the different tests that we have. In this case, we have two examples. We're testing calculate price and also load data, which both need an object of Produce Insights. So in this case, we can see that it's just passed in as an argument within each of these tests here, which is great because we don't even have to specify it within the arrange section because it's coming in already as an input argument. Another great thing about fixtures is that you can modify the scope depending on what's appropriate or needed for your testing. So if you have, let's say, a suite of code, you have like 10 Python, like .py scripts, and they're organized in a certain way. But let's say there's a certain object that you're using quite a bit throughout those different sorts of those different files. You can actually specify a fixture outside of your test file in a different file and then just import it and kind of use that across different tests as well. So really great. It's not contained to just within one single test file. Okay, so next up, we have parameterization. So I personally find this really helpful, especially for working with data, since there's a lot of different cases we will work with. The same function will need to work with different sorts of, different values, and the expected output, the way it's processed should be the same, but we want to make sure we can work with that data. So for parameterization, it's a way of being able to point out different sets of that input to pass through a function without having to write multiple tests. So instead of saying test load data 1, test load data condition 2, test load data condition 3, and having a different method for each of those, we can just have one test load data and set in sets of parameters. So with this example, we have at the top, we're marking this as parameterization. These two things here are the different arguments that we're parameterizing for this test. For this test, we are loading in first data path, and then also expected error type, since we're testing exceptions in this case. So let's say for load data, we need the path as something that goes into the function itself. And in this case, we can see that we're testing it or passing in 3 sets of input. First, we have some non-existent CSV file, another non-existent CSV file, et cetera, since we're testing exceptions. And then second, within each of these pairs is the expected error type that we would see from this given input. So just in general, when it comes to parameterization, you first set a string that lets us know what the arguments we're going to be passing in are, what they're called. And then following that, we have a list just showing different tuples of that input sets. And so this is actually parameterizing what's being sent into the test method itself. So as we can see, At first, we have the produce fixture, as we saw in the previous few slides, being identified first. And then after that, we see the different arguments from parameterization being passed in. So here we can see that data path here corresponds to data path within this test argument. And expected error type here corresponds with expected error type here within the arguments for the test. So this is particularly helpful for multiple cases. When you're working with a happy path, for example, you may want to add in, let's say, 3 different sets of input that are kind of general sorts of data that you would expect. And then maybe you also want to put in a few different edge cases that you would expect to not lead to failure, but still be processed correctly. So that's a great way to test multiple conditions. Building upon this, we saw that this was an exception test rather than a happy path test. So just to kind of reiterate, happy path is when you feed in input that you expect to work properly, and you would expect the output to be, whatever you expected. But for exceptions, that's when the input into the method you're testing would lead to some sort of error. And so in this case, this is the same as what we saw on the previous slide, but now we can see further down that the test itself has an empty range because there's nothing we really need to kind of prepare. And then when it comes to act, we're feeding in that data path that is being parameterized. So the first time this test is run, this set non-existent file .csv is passed in. So once that's done, the way that this is formatted is such that when an error is thrown, we kind of collect what error type that is, and we're going to compare that against the expected error type. There may be different ways that you want to actually test exceptions, but this is just a simple way. So this is helpful in cases where, by default, let's say there's some sort of situation with your method that would fail. But by default, the error message that you get from whatever small minor thing that fails is not really helpful for the user to understand what's actually going on. So when you write specific exception raises within your code itself, this is just a test to make sure that those expected error messages are provided back to the user. Okay. All right. So the next concept is something that took me a while to get used to, so it's going to take a few more slides. Looking back, it's actually not all that bad, but I think I struggled quite a bit with it at the start because the documentation was didn't really cover everything extensively from a data scientist lens. And so I want to be able to share this in a way that hopefully is easily digestible for everyone. I think the trickiness really comes more about the implementation and specific tricky things that happen here and there when you need to use this in a real-world setting. But in this example, let's look at one of the methods within our class itself. Not a test. This is just something within Produce Insights. So here, we have our method that we're going to be testing. Let's call this process and update data. So we're going to consider this our primary method that we want to test. We can see that within here, it takes in some arguments, argument 1, argument 2, processes the data some way. And the way that it does that is it calls another method within itself, within the Produce Insights class called calculate price. And then it applies some complex transformation that's actually an imported method from some other file or some other library. Then lastly, we're going to update the results that are attached to the object itself. So this is a very simple example, but the general concept here definitely is applicable for all sorts of situations. So here we can see that there's intermediary methods, or we can call them secondary methods, within our primary method. But when it comes to testing we are interested in just testing this main method. We're not necessarily interested in testing the smaller methods that are within it. So how do we go about this? So this is where mocking comes into play. So mocking is a way of essentially preventing calls to those intermediary functions and instead just patching it with some sort of expected return value. So when it comes to the test, as we see on the right, with the test, we can see that a mocker object is passed into the test itself. So this is something that is just available through PyTest mocker. And so you just pass this in, and within your arrange section, in addition to preparing the inputs to the to the function, you'll want to do your mocker.patch calls as well. So how this works is with mocker.patch, you specify the specific method that you're going to be mocking. So in the case of the code we were looking at previously, this was located in the source folder, source utils produce.py. And within produce.py, we had the produce insights class. And within that, we had calculate price. So that's pretty straightforward. We have the kind of linkage to that specific method there. And we're going to say that for that intermediary function, calculate price, we're just going to return an empty data frame. Similarly, for the complex transformation, we're going to be doing the same thing. But note that here, we can see it's source utils produce.complex transformation. But the original location of this complex transformation is somewhere else. If you note back from a few slides ago, complex transformation was imported from some other location. But what we're putting here is the specific reference to it within the class that we're working with, not the original location. And so similarly here, we're specifying an output data frame of being empty. So instead of actually running this, we'll just be returning this. And so when it comes to these mocker.patch calls, we want to make sure that they're actually called, and that's what we can do in the assert section, in addition to asserting that the actual outcome is what we expect it to be. So what does this actually look like? Let's go back to that method. So here's that original code that we're looking at before. And if we apply those mocker.patches, it's effectively this. So you can see that the calls to those methods are replaced with whatever return values we specified. And this is really great for ensuring that we're testing what we want to test and also reducing test time as well. Let's say a complex transformation is something that takes like multiple minutes. We don't want to have to run that every single time we're running a test of process and update data, especially for running multiple sets of input for this test itself, because that can really escalate quickly. So this is a great way to ensure that we are specific in what we're testing and also saving time as well. All right. And so mocking's great, but it's not something we should do absolutely every single time we're working with something. So we want to ensure that when we're mocking, we do want to mock imported library calls, so things like, I don't know, anything like scikit-learn or PyTorch and things like that. If it's like an actual imported function from a library that exists, we'll want to mock that because usually those are already tested. When it comes to code that we've already written that has tests written for it as well, we can mock those like in the example we just provided. And any sort of calls to external services, we also typically want to mock, given that tests should be able to run locally. If you have any sort of connection to a database, for example, as part of your data loading, or any sort of external calls like that, API calls, you want to be able to mock those so you don't need to do those external connections. So we can talk more about that as well than Q&A or office hours. However, you do not want to mock really basic things that are essential to the operation of your function that you're testing itself. So if you have any sort of methods that you don't have tests for yet, write those tests, don't mock those yet. And any sort of basic operations, so let's say getting like shape of something, addition or whatever, you don't need to mock like the small things. So when it comes to mocking, it's really crucial, but you also don't want to go overboard with what you're kind of patching out. And I'll hold here just for a second as the photo's being taken. Sorry. All right. And then, all right, so we're running a little fast, apologies, but this leaves more time for questions. So just in overview, the value of unit testing for data science code is that it really helps for writing production-ready code. There's more to it than just unit testing, but it is really a key part of it. It helps promote quality for any sort of solutions you're writing for yourself or with others, and it helps prevent downstream headaches as well. I will say there's multiple instances where unit testing really helped me clean up, like notice certain situations with my code where, let's say, I wasn't accounting for a particular edge case, or I accidentally hard-coded something and that was affecting the results downstream. Like this was a great way to catch that ahead of time and prevent any sort of downstream headache. And lastly, in a collaborative environment, essential and really, really helpful. So when working with other people's code, when working with your own code down the stream as well. It's been really, really helpful for that. And for example, any sort of contributions to open source libraries as well, or for any sort of solutions you're writing, you'll want to have unit tests. So just as a takeaway is that unit testing is not just for software engineers, but for data scientists too. So I want everyone here to feel confident in their ability to start writing tests if you're not already. And if you have been writing tests, hopefully what I've shared has been helpful. And I want to have this slide up real quick for anyone who might want to take pictures for resources that are helpful. So the example code that I use within this repository is also available at source 3. There's just a lot of different resources now available for this that weren't available a few years ago. So definitely take a picture if you have a moment and are interested in this. And hold that up. All right, I think one other person's taking a picture. Okay. All right, and just want to say thank you, everyone.